Hi, this is Mrs. Basin, and in this screencast we're going to talk about balancing chemical reactions, or balancing chemical equations. So when we have a chemical reaction, this is the general form for a chemical reaction. The reactants are always on the left, the products are on the right, and for now we're just going to look at reactions that happen in one direction. So the reactants are what we start out with, and the products are what we end up with. And that arrow that you see there in chemistry, we call that a yields sign. The other thing that can be included in a chemical equation are the physical states of the reactants and products. So if something is in the solid state, you'll see a little S next to it. If something's in the liquid state, you'll see a little L. If something's in the gaseous state, you'll see a little G. The other thing that you could potentially have is something in the aqueous state, which means that it is something that's dissolved in water. Now, this is when we talk about solutions, the most common solutions are aqueous solutions. But just take note that you can have solutions in other things, like there are some substances that dissolve better in acids or in alcohols. So not every solution is an aqueous solution, but the most common ones are. So just as an example, here's an example of a reaction to show with the physical state. So let's say we have sodium metal, that's a solid, that reacts with water, which is a liquid. So we put a little L there. When those are reacted together, that yields sodium hydroxide, which is aqueous, so you get a little AQ there, and hydrogen gas, which gets a little G. Okay, so that's what those little symbols mean. And when you see the solid, the liquid, and the aqueous, and the gas, that just means that's the physical state of the reactants. Okay, now when there is a chemical reaction taking place, there are several things you can look for. Not every time you mix things together do you get a chemical reaction. So for example, some physical changes are things like if you take salt and you dissolve it in water. That would be a physical change. There's no chemical reaction going on. All you're doing is taking solid salt and you are making an aqueous salt solution. So you could boil the water off and the salt would still be there. Some other examples are if you take an ice cube and you melt it. So you're going from solid water to liquid water, but it's still water. If you take that water then and boil it, now you're going from liquid water to gaseous water, but it's still the same substance after you have given it whatever treatment you did to it. So when you have a chemical reaction, there are new substances produced. So there are several things we can watch for as we are looking at a reaction to decide whether it is indeed a chemical reaction. So the first thing we can look for is heat being released or heat being absorbed. In the most obvious form, the reaction would get very hot if there was heat released, and it would get cold if there was heat absorbed. Now, it's not always that obvious. Sometimes it's a very slight change in temperature that would take a thermometer to actually record the difference, but sometimes you will actually see the heat being evolved from the reaction, or you will feel the reaction getting cold. If you have a reaction where there is heat released, we call that an exothermic reaction. So that's heat being released. So EX mean exit. Exo you can think of as meaning exit. So heat is exiting. Therm, if you think of other words you know that have therm in them, like thermometer, thermostat. So that has to do with heat and temperature. So that means heat is exiting if it's exothermic. If it's endothermic, you can think of it as it's being absorbed or it's going into the system. Light being produced is another one. So if you see a light produced as a result of a chemical reaction, if you imagine like popping a glow stick or breaking a glow stick and setting off that reaction, that light is coming from the reaction itself. Gas being formed is another great indicator of a chemical reaction. If gas is being formed in a solution, you'll see bubbles. If you have a gas and you're trying to decide what it is, most gases are colorless. If you see a colored gas, that means it's a poisonous gas, so we would not be doing any of those in the lab. But if we have colorless gases, there are several different tests that we can do to decide which gas it is. If you have hydrogen gas will give off a barking noise or a squeaky pop noise when you take a burning splint and put it in the presence of hydrogen gas. Another gas we might have is oxygen gas. Oxygen gas, if it is there, will relight a glowing splint. And then the other gas we could potentially have is CO2. And CO2 if you have CO2 present, it would extinguish a flame. So we'll do a lot more with those in class, but those are just some examples of how we could test to see which gas is actually produced. The last one is you can have the formation of a precipitate. So what a precipitate is something insoluble or a solid that's formed when you have solutions and you mix those together. So when you have chemical reactions, they have to be balanced. Because of the law of conservation of matter, we can't create matter or we can't destroy matter. So when we write out a chemical reaction, everything has to be accounted for on both sides. So when you write these reactions, you have to have the same number of atoms on each side of the equation, in the reactants and in the products. So we're going to go through and do a couple examples of how to balance these equations. There's a very systematic way of going through this. Of course, there's more than one way, and you can always go look for other ways, or I can show you other ways in class. This is what I believe to be, in the beginning, the simplest way to learn how to do this. So what you do is, this is your overall equation that has been given here, and eventually we'll get to where you can actually write these out yourself. But the way to start this is under the yield sign, which we said is our arrow, we're going to write which elements we have present. So we have sodium, we have hydrogen, and we have oxygen. So those are our three elements, and if we look on the other side, we also have sodium, hydrogen, and oxygen. If at this point you get to where you have different elements on both sides, then there's something wrong with your chemical equation, and you want to go back and check that first. Okay, our next step would then be to count, let me change colors here, would be to count how many atoms we have on each side. So if we start on the left, if there's no number in front, we're going to assume those are ones. The other important thing that I failed to mention is that you can only add coefficients to balance the equation. So you can only put numbers in front of the elements or the formulas. You can't change the subscripts, because if we start messing with the subscripts, then we're actually changing the substances that are involved, and we can't do that. So the only thing we can add are coefficients. So if there are no coefficients there, that means that there's a 1 there that we don't have to write. So if we start on the left again, we're going to count and see how many atoms of each we have. So we have 1 sodium, we have 2 hydrogen, and 1 oxygen. Then if we go to the right, 1 sodium, 2 plus this one over here, so we have 3 hydrogen, and then 1 oxygen. Okay, then at this point, we're going to look at this, and it's pretty much a guess and check method, to where we're going to add a coefficient somewhere, and then we're going to recount and see how that changes everything. So if I notice here, right now, my only thing that is not balanced is my hydrogen. So I know that somehow I'm going to have to fix that. Now if I look, if I have a 2 over here, every number we put in front of there has to be a multiple of 2, so that means this has to end up being some even number. So we have to figure out a way to get an even number over on this side. So let's say I put a 2 in front of here. Okay, so when I do that, that's not only going to change hydrogen, it's also going to change sodium and oxygen. So I'm going to recount everything it affects. So I'm going to cross out this 1, and I'm going to completely recount my sodium. So now I have 2 sodiums. If I recount my hydrogen, I now have 2, because this 2 gets distributed to the whole thing, so there's 2 there, plus these 2 over here, so now I have 4, and then now I have 2 oxygen, because again that 2 goes to this whole compound. So now I'm going to go back to the other side and fix the things that got changed as a result of what I did on the right. So sodium now, that's an easy fix. I can just put a 2 in front of there, so now I have 2 of those. And then to fix my hydrogen, since I have 4 on the right, I'm going to put a 2 in front of these, again only changing coefficients. So I'm going to recount that. Now I have 4, and then I have 2 oxygen. So now I have 2 and 2, 4 and 4, 2 and 2, so that means that that one is balanced. Okay, let's look at another one. So if we look at this one looks kind of scary. It's got a lot of different stuff going on here, so let's make a list of everything we have. So I have sodium, I have hydrogen, I have carbon, I have oxygen. Okay, so those 4 elements cover everything we got going on here. So sodium, if I start on the left, I have 1. Hydrogen, I have 1 here, and 3 here, so a total of 5. I forgot to change my color here. I'll do that in a second. Carbon, I have 2 plus this 1 is 3. Oxygen, I have 3 here, plus this 2 is 5. Okay, then on the other side, I've got 1 sodium again. Hydrogen, 3 plus this 2 is 5. Carbon, 2 plus this 1 is 3. Oxygen, 2 plus 2 plus 1. I have 5. So if we look at this one, I've got 1 and 1, 5 and 5, 3 and 3, 5 and 5. This one is already balanced. So as bad as that looked in the beginning, I don't have to do anything to this one because this one is good the way it is. Okay, so let's look at 2 more examples here. So if I go to my one in the top, this is the decomposition of hydrogen peroxide. And these are all demonstrations that we either watched videos of or that we did in class, so that you have some reference point for most of these. So if we look at this one, we've got H and O on both sides. So then I'm going to count my elements on the left, 2 H's, 2 O's. Over on the right, 2 H's, and then 1 plus 3 O's. Okay, so same situation here where I've got 2's and 2's, so I know I have to somehow get an even number of oxygens. So let's say I start out with a 2 here. So if I do that, 2 times 2 is 4. 2 times my oxygen is 4. So now I have an issue with hydrogen, so I'm going to go back over to the other side, put a 2 in front of there. 2 times 2, that takes care of that, is 4. Then I end up with 2 oxygen here, plus these 2 gives me 4, so just changing that one thing took care of everything. So I've got 4 hydrogen on both sides, 4 oxygen on both sides. That makes it balanced. Okay, last one. This one is the production of hydrogen gas by reacting zinc metal and hydrochloric acid. So I have zinc, I have hydrogen, and I have chlorine. I'm going to count 1 of each on the left, 1 zinc, 2 Cl, 2 H's on the right. Okay, so this one, I have to fix my hydrogens and my chlorines. So if I look over here, by putting a 2 there, recount my hydrogens, that makes that 2. Recount those, makes that 2. So that's all I had to do for that one to make it balanced.